in many technical ways, and I wish I could give you a number of them. I'll give you some very simple ones to show you how, from the conservation of energy and knowing the formulas for the energy, which are not those, you can calculate, you can see what some certain things have to happen. In other words, many laws are not independent laws, but are just secret ways of talking about the conservation of energy, or better. Knowing the conservation of energy, you can understand a lot of laws. The simplest one is a lever. If this is a lever on a pivot, and let's say this distance is 1 and this distance is 4 times 1 foot and 4 feet, then first I must give you the law for gravity energy. And the law for gravity energy is to take, if you have a lot of weight, you take the weight of each weight and multiply it by the height above the ground and add this together for all the weights, and that gives all the gravity energy. Now let's put the ground right here. I have a 1 pound weight here, just to make it, or say to make it more complicated, 2 pound weight here. And I have an unknown mystic weight on the other side. X is always the unknown. So let's call it W to make it look more, that we've advanced above the usual. Now, the question is, how much must W be so that it just bounces and swings quietly back and forth without any trouble? That means that the energy, if it swings quietly back and forth without any trouble, when it's set this way, and when it's tilted up a little bit, say, for instance, if this has gone up 1 inch, the energy is the same. If it is the same, then it doesn't care much which way, and it doesn't fall over. So if this goes up 1 inch, how far down does this go? If you think about it quite a long time, this being 1 inch and that being 4 feet, you can figure out by proportion that this being 1 foot, this is 1/4 of an inch. So that the rule says this, that before anything happened, all the heights were 0, so the total energy is 0. After the thing has happened, we multiply the weights, unknown, by the height, minus 1/4 of an inch, add the other weight, 2, by the height, 1 inch, and this should add up to the same energy as before. So that 1/4 of W taken away from 2 is 0, and W must be 8. So that's how we find the laws. I mean, that's one way we can understand the easy law that you know, of course, the law of the lever. But it's interesting that not only this one, but hundreds of others of the physical laws can all be closely related to the various forms of energy. So I illustrate that only to illustrate how useful it is. The only trouble is, of course, it doesn't really work. I mean, if you did that, it wouldn't swing like this on account of friction in the fulcrum. If I had something moving, for instance, it has kinetic energy like a rolling ball, and it's on a constant height, and it rolls along, and then it stops. That's on account of friction. But what happened to the energy of the ball? And the answer is that the energy of the ball has gone into the energy of the jiggling of the atoms in the fluorine in the ball. The world that we see on a large scale looks so nice when we polish a nice round ball and so on. It's really quite complicated when you look at it on a little scale. Little billions of tiny atoms with all kinds of irregular shapes looked at in detail. It's like a very rough boulder, really, when looked at finely enough, because it's made out of these little balls. And the floor is the same way, as a bumpy business made out of balls. And you roll this monster thing over the other. You can see that the little atoms are going to go snap, jiggle, and after the thing has rolled across, the ones that are left behind are still shaking a little bit from the pushing and snapping that they went through. So there is left in the floor a jiggling motion or thermal energy. And although at first it looks like the law of conservation is false, energy has a tendency to hide from us, and we need thermometers and other instruments to make sure that it's still there. The first demonstration of the conservation of energy, the energy is conserved no matter how complex the process, or no matter what, even when we don't know the detailed laws. The first demonstration of the law of conservation of energy, in fact, was not by a physicist, but by a doctor, a medical man. He demonstrated with rats that the total energy of the food put in before and the heat generated by you burn food and you find out how much heat is generated, and then you feed the rats the food, and it's converted an oxygen and it's converted to carbon dioxide the same way as in burning. and measure the energy in that case, and you find out that living creatures do exactly the same thing as non-living creatures. That the law of conservation of energy is exactly as true for life as not. As a matter of fact, it was discovered by this. Incidentally, it's interesting that every overall principle that we know that we can test on the great phenomena of life work just as well as for dead things. That is, there is no evidence yet that what goes on in living creatures is necessarily different, or maybe more complicated, but that is necessarily different than what goes on in non-living things. I mean in the physical, as far as the physical laws are concerned. Incidentally, this amount of energy that's in the food, it'll tell you how much heat and mechanical work and everything that's generated is what you read. When you read up here about calories, you're not eating something called calories, but you're eating that measure of the amount of heat energy that's in the food. For people who like to, if physicists always feel so superior and smart and so on, that people would just like to get them once on something, and so I'll give you something to get them on. They should be utterly ashamed of themselves, because they take the same thing, energy, and they measure it in a host of different ways with different names. Absolutely absurd. Energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTU, in horsepower hours, in kilowatt hours, all exactly the same thing. It's like having money, you know, in dollars and in pounds and so on. But unlike the economic situation where the ratio can change, these dopey things are an absolutely guaranteed proportion. If anything could be analogous to it at all, the only hope would be to say that there are 20 shillings to a pound, and that you have shillings and pounds, with one complication that the physicist allows, in that instead of saying he has 20 shillings to a pound, he says he has irrational ratios like 1.6183178 shillings to a pound. So, in addition to that, you'd think that the more modern, high-class theoretical physicists would at least use a common unit, but you can find papers with degrees Kelvin for measuring energy, megacycles, inverse Fermis is the latest invention. We don't need any more inventions. We should all measure the energy in exactly the same. We should measure the energy in one unit and let it be done instead of having all these different names. And it just shows, and people are often also, they want to say, see, I should bring my little boy to show on the screen so that the audience will understand that I'm human. Well, the proof that physicists are human is the idiocy of all the different units which they use in measuring energy. Now, we have a number of interesting phenomena in nature which present us some curious problems with energy. Has recently been discovered things called quasars, which are very far away and they emit a lot of light. They're enormously far away, emit a lot of light and a lot of radio waves, and have radiating so much energy that the question is, where does it come from? That is, after it's radiated this enormous amount of energy, the condition must be different than it was before, if the conservation of energy is right. Question, is the thing collapsed gravitationally? Is it different condition gravitationally? Is it coming from gravity energy, this big emission? Or is it coming from nuclear energy and so on? And nobody knows. Will you like to propose that maybe the law of conservation of energy is not right? Well, when a thing is investigated as poorly, I don't mean as incompletely as is the quasars, because they can't see so easy at such a large distance, it very rarely is, when a thing looks difficult, that the fundamental laws are wrong. It's usually that the details are unknown. Another interesting example of the use of the conservation of energy is in this reaction. It was first thought that neutrons turn to protons plus electrons. But the energy of a neutron is fixed, and that of a proton could be measured, and the energy of an electron did not add up correctly to the energy of the neutron. If the proton and electron together didn't add up to the neutron. Two possibilities existed. One was the law of energy conservation is not right. In fact, it was proposed by Bohr for a while that maybe the conservation law worked only statistically on the average for large scale. But it turns out that Pauli suggested no, that the fact that the energy doesn't check out is because there's something else coming out, which we now call an antineutrino, and that this other thing coming out takes out the energy. You say the only reason for the antineutrino is to make the conservation of energy right. Well, it takes a lot of other things right. Conservation of momentum and other conservation laws are fixed up because a piece came out that we weren't worrying about. And very recently it has been directly demonstrated that such neutrinos indeed exist. That illustrates a point. Why are we able to extend our laws to regions that we're not sure How is it possible? Why are we so confident? Because we check the energy conservation here, then when we get a new phenomenon, we say it's got to satisfy the conservation of energy. And every once in a while you read in the paper that the physicists have discovered one of their favorite laws is wrong. It's not a mistake to say that it's true in a region where you don't look yet, when you haven't looked yet. If you will not say that it's true in a region that you haven't looked yet, you don't know anything. If the only laws that you find are those which you just finished observing, then you can't make any predictions, and the only utility of the science is to go on and to try to take guesses. You see, the most likely thing is that the energy is conserved in other places. So what we do always is to stick your neck out. People like this, and that of course means that the science is uncertain. The moment that you make a proposition that about a region of experience that you haven't directly seen, then you must be uncertain. But we always must make statements about the regions that we haven't seen, or there's no use in the whole business. For instance, in early experiment, the mass of an object changes when it moves because of the conservation of energy. The energy associated with the motion appears as an extra mass because of the relation of mass and energy. So things get heavier when they move. It was first believed by Newton that this wasn't the case, that the masses stayed constant. And so when it was discovered that that was false, everybody say it was a terrible thing the physicists found out they were wrong. Why did they think they were right? The effect is very small. Only when you get near the speed of light does it make any difference. If you spin a top, it weighs the same as if you don't spin it within million, very, very fine fraction. So you could say, oh, they should have said, if you do not move any faster than so-and-so, then the mass doesn't change. That would then be certain. No. The experiment happens to be done only with tops made out of wood, copper, steel, and so on. So we should have said that tops made out of copper, steel, wood, and so on were not moving any faster. You see, we do not know all the conditions that we need for an experiment. It is not known whether a radioactive top would have a mass that's certain, but we have to take a guess. So in order to have any utility at all to the science, in order not simply to describe an experiment that's just been done, we have to propose laws beyond their range, and there's nothing wrong with that. That's the success. That's the point. And that makes the science uncertain. If you thought before that science was certain, well, that's just an error on your part. Now there are so we have here the energy, which we could put in our list. And it's conserved perfectly as far as we know, but it does not come in units. And now the question is it the source of a field? And the answer is yes. Einstein understood gravitation as being generated by energy. Energy and mass are equivalent, and Newton's interpretation that the mass is what produced the gravity has been modified to being the energy that produces the gravity. There are other laws that are similar to the conservation of energy in the sense that they're numbers. I haven't very much time to describe them, but I'll mention what they are. One of them is the momentum. It means if you take all the masses in an object and multiply them by the velocities, for instance, and add it together, that's the momentum of the particles in it anyway. And that total amount of momentum is conserved. The energy and the momentum are now understood to be very closely related, and so I should be in the same column in this conservation law. Another example of a conserved quantity is angular momentum, an item which we discussed some time before. The angular momentum is the area generated per second by objects moving about. For example, if an object is here and is moving, and we take any center whatsoever, then the area, the rate of change, the speed at which this area increases, multiplied by the mass of the object, and added together for all the objects, is called the angular momentum. And that quantity doesn't change either. So we have conservation of angular momentum. Incidentally, at first sight, if you know too much physics, you might think that the angular momentum is not conserved. Like the energy, it appears also in different forms, although most people think it only appears in motion. But it does appear in other forms, and I will illustrate that. You know that if you have a wire and move a magnet up into it, increasing the magnetic field through the flux through the wire, there'll be an electric current. That's how electric generators work. So now imagine that I have, instead of a wire, a disc on which there are electric charges.